The more you know, the more you realize you know nothing. These wise words from physicist Edward Teller ring especially true in our age of information. We live in a world where data is constantly being generated, from the tweets we send to the scientific discoveries we make. This data holds the key to understanding our past, navigating the present, and shaping our future. But what happens when we run out of space to store it all? Every day we produce an astronomical 2.5 quintillion bytes of data. That's a 1 with 18 zeros after it. Our current storage technologies, reliant on silicon chips and magnetic platters, are struggling to keep up. Hard drives, though constantly evolving, have physical limitations. They're also susceptible to damage and degradation, putting our precious data at risk. Imagine trying to fit the entire Library of Congress onto a single thumb drive. That's the scale of the problem we're dealing with. We need a new storage solution, something revolutionary, something biological. Enter DNA, the blueprint of life itself. This microscopic molecule, tucked away in the nucleus of every cell, holds the genetic instructions for all living organisms. What many people don't realize is that DNA is also an incredibly efficient storage system. DNA can store information with astonishing density. A single gram of DNA can theoretically hold up to 215 petabytes of data. That's equivalent to millions of gigabytes. Furthermore, DNA is incredibly durable. It can last for thousands of years under the right conditions, preserving our data for future generations. But how do we go from digital ones and zeros to the language of DNA? This question has intrigued scientists and researchers for years, leading to groundbreaking advancements in the field of biotechnology. It's a fascinating process called DNA encoding. This process is not just a theoretical concept, but a practical application that has the potential to revolutionize data storage. First, digital data, like a photo or a text file, is converted into a DNA sequence. This step involves sophisticated algorithms and software that can handle large amounts of data efficiently. This involves translating the binary code, ones and zeros, into the four-letter alphabet of DNA, A, T, C, and G, which represent the four chemical bases of DNA. Each binary digit is mapped to a specific DNA base, creating a unique sequence. Think of it like translating English into Morse code, but instead of dots and dashes, we use the building blocks of life. This analogy helps us understand the complexity and elegance of the process. This encoded DNA sequence then serves as the blueprint for creating synthetic DNA strands. These synthetic strands can be stored for long periods, offering a durable and compact solution for data storage. The potential applications are vast, from archiving historical records to storing personal data securely. Section 5, from digital data to molecular libraries, synthesis and storage. Once the data is encoded into a DNA sequence, the next step is to synthesize or write this information into actual DNA molecules. This process is akin to translating a digital file into a biological format, bridging the gap between the digital and the molecular worlds. This is done using a process called DNA synthesis, where scientists can build custom DNA strands base by base, like assembling a microscopic Lego set. Each base, represented by the letters A, T, C, and G, is meticulously added to form sequences that encode the desired information. These synthesized DNA strands are then stored in tiny vials, essentially creating miniature libraries of information. These vials are carefully labeled and catalogued, ensuring that the data can be easily accessed and retrieved when needed. The beauty of DNA storage is its compactness. Unlike traditional storage devices that require significant physical space, DNA can store vast amounts of data in an incredibly small volume. Imagine storing the entire global internet archive in a space the size of a sugar cube. This revolutionary approach not only saves space, but also offers a durable and long-lasting storage solution. DNA, being a stable molecule, can preserve information for thousands of years under the right conditions, making it an ideal medium for long-term data storage. As technology advances, the efficiency and cost-effectiveness of DNA synthesis and storage are expected to improve, potentially transforming the way we think about data preservation. This cutting-edge field holds promise for a future where our most valuable information is stored in the very building blocks of life itself. Section 6. Unlocking the secrets, retrieving data from DNA. Now, how do we access the information stored in these DNA molecules? It's like reading a book from the library of life. Retrieving data from DNA involves a process called DNA sequencing. This involves reading the sequence of base pairs in the DNA strand and converting it back into digital information. Think of it like translating that Morse code message back into English. Advanced sequencing technologies are making this process faster and more affordable. Section 7. DNA Data Storage in Action, Advancements and Examples. DNA data storage is not just a futuristic concept, it's already happening. In 2012, researchers at Harvard University successfully stored a 52,000-word book in DNA. More recently, Microsoft and the University of Washington collaborated to store 200 megabytes of data in DNA, including the Universal Declaration of Human Rights in over 100 languages. These breakthroughs demonstrate the incredible potential of DNA data storage to preserve our collective knowledge and cultural heritage for generations to come. Section 8. The hurdles to overcome: cost and speed. While incredibly promising, DNA data storage does face some challenges. The biggest hurdle is cost. Synthesizing and sequencing DNA is still relatively expensive, making it impractical for everyday use. Additionally, the process of encoding, writing and reading DNA data can be time-consuming compared to the rapid-fire access of our current digital storage devices. However, as research progresses and technologies improve, we can expect the cost of DNA data storage to decrease and the speed to increase, just like we saw with the evolution of computers and smartphones. Section 9. DNA data storage, a glimpse into the future. The future of DNA data storage is brimming with possibilities. Imagine a world where the very fabric of our existence, our DNA, becomes the foundation for storing vast amounts of data. This isn't just science fiction, it's a rapidly approaching reality. Libraries, the bastions of human knowledge, could soon store vast archives of books and historical documents in DNA. This method would preserve them for millennia, far surpassing the longevity of traditional digital storage methods. Imagine walking into a library where every book, every piece of history is encoded in the very essence of life. In the medical field, hospitals could back up patient medical records in DNA, ensuring their availability for future generations. This would not only safeguard critical health information, but also revolutionize how we approach medical data storage, making it more secure and durable than ever before. We use DNA to create ultra-compact, energy-efficient data centers. These centers would occupy a fraction of the space of current facilities and consume significantly less power, addressing some of the most pressing issues in data storage today. Imagine a data center the size of a sugar cube holding the entire contents of the internet. DNA data storage represents a paradigm shift in how we think about data. It's not just a new method, it's a revolutionary approach that leverages the natural world's efficiency and compactness. This technology could change everything, from how we store personal memories to how corporations manage vast amounts of information. It's not just about storing more information. It's about preserving our collective memory and unlocking new frontiers in biocomputing. The potential applications are vast, from archiving cultural heritage to enabling advanced computational processes that were previously unimaginable. As we continue to explore the vast potential of this microscopic marvel, one thing is certain. The integration of DNA into our data storage solutions will open doors to innovations we have yet to dream of. Scientists around the world are working tirelessly to overcome the current limitations and make this technology accessible on a global scale. DNA is poised to revolutionize the way we store and interact with information for generations to come. This isn't just an incremental improvement, it's a leap into a future where data storage is as natural and enduring as life itself. The possibilities are endless, and the journey has just begun.